All right, let's just jump right into this explainer. This aircraft isn't just another plane. I mean, it is arguably the ultimate engineering triumph of the 20th century, the SR-71 Blackbird. Today we're going to really look closely at the impossible brief that brought it into existence, and we'll break down the exact source material to understand the three main technical challenges engineers faced, and exactly how they solved them to build an absolute legend.
Mach 3.2, 85,000 feet. Just let those numbers sink in for a second. Back in 1976, a manned, air-breathing aircraft actually set these absolute speed and altitude records. And honestly, the most astonishing fact? Here we are today, half a century later, and those records remain completely, 100% unbroken.
Now, this whole thing didn't just start because someone wanted to go fast. It actually started with a really dire problem. Back in May 1960, CIA pilot Francis Gary Powers was flying a U-2 reconnaissance aircraft over the Soviet Union at about 70,000 feet. At the time, everybody assumed that altitude was totally untouchable by Soviet air defense. Well, that assumption was tragically wrong. A Soviet S-75 surface-to-air missile reached him anyway. So literally in a single afternoon, the United States lost its primary intelligence asset. And for Lockheed's Skunk Works division, the takeaway was stark. Altitude alone just wasn't a safe harbor anymore.
So that led to a totally new, completely uncompromising engineering mandate. The brief wasn't to build an aircraft that was, just difficult to intercept. It was to build an aircraft that is physically impossible to catch. That meant sustained cruise speeds of Mach 3 at altitudes exceeding 80,000 feet. They needed to fly so fast and so incredibly high that no missile could physically be launched, climb, and reach the aircraft before it had already vanished.
That extreme speed mandate? Well, it created three totally unprecedented engineering problems. Let's start with Challenge 1, the material.
So at Mach 3, the aerodynamic friction is so intense that it heats the leading edges of the airframe to temperatures well over 500 degrees Fahrenheit. Standard aluminum, which is what we normally make planes out of, loses its structural integrity way below that threshold. It would literally melt in the sky. Because of that, engineers had to pivot to an exotic titanium alloy. Titanium retains its strength under extreme heat and has a super low thermal expansion rate. Because of this necessity, a staggering 85% of the SR-71's structural mass had to be fabricated from titanium. But getting that titanium, that introduced a massive historical paradox. The United States actually didn't even possess enough domestic titanium ore to build a fleet of these things. You know who did? The Soviet Union. So operating through this covert network of front companies, the CIA quietly purchased the necessary raw material from the exact nation the aircraft was being designed to spy on. You really can't make that up.
Even after they got the metal, actually fabricating it proved just as difficult as smuggling it. Early on, the rejection rates for delivered titanium components hit an unbelievable 80%. Why? Because the titanium turned out to be wildly sensitive. Engineers realized that just washing the welded parts with standard tap water caused corrosion. The trace chlorine in the water was actually attacking the metal on a molecular level. They had to completely switch to distilled water. They even banned cadmium-plated tools from the production floor entirely, because simply touching the titanium with those tools ruined it.
Okay, this is probably my favorite detail regarding the material challenge. Because of the insane heat of Mach 3, the fuselage panels were deliberately manufactured to fit loosely at ground temperature. There was literally no flexible sealant on Earth that could survive the operational heat. So sitting there on the runway, the aircraft literally leaked JP-7 fuel onto the tarmac. But at cruise speed, the intense thermal expansion stretched the airframe several inches, perfectly closing every single gap. The extreme operating condition of heat was actually the missing puzzle piece that structurally sealed the plane.
All right, that brilliantly solves the material issue, which brings us to Challenge 2, the propulsion.
The Pratt & Whitney J58 engine is definitely not your conventional jet engine, mostly because at Mach 3, it simply can't afford to be. The massive problem they had to solve here is called inlet management. At Mach 3, the air entering the inlet is moving at about 2,200 miles per hour. If you feed that directly into a normal compressor, it will destroy the engine immediately. So the J58 uses a variable geometry inlet spike, basically this large cone that physically pulls backward as the speed increases. This constantly recalculates the shock wave, effectively decelerating the air to a speed the engine can actually swallow. This inlet management system builds into a really genius three-step process, where the J58 essentially transforms its own operating principles right in the middle of the flight. First, at lower speeds, it just operates as a standard turbojet. Second, as it pushes past Mach 2.5, bypass ducting actually opens up, routing the incoming air around the turbine core and sending it directly into the afterburner. Finally, by the time it hits Mach 3.2, the engine has morphed and is functioning as a partial ramjet.
And this leads to what I think is the most mind-boggling stat about the propulsion in the source material. By the time the Blackbird is cruising at Mach 3.2, that physical inlet spike itself is generating 54% of the total thrust. The actual engine core and turbine become totally secondary, generating only 46%. The aerodynamics of the inlet are literally doing the heavy lifting.
But if that delicate inlet management failed, the consequences were absolutely brutal. They called it an engine unstart. If the shockwave was ever expelled from the inlet, the afterburner would immediately extinguish, and that sudden asymmetric thrust would violently yaw the aircraft. It was so abrupt and aggressive that the pilots' helmets would literally smash into the cockpit canopy. Digital inlet control systems eventually helped tame this, but the underlying physics of Mach 3 remained totally unforgiving.
So they solved the material, and they built the engine. Moving on to our final hurdle. Challenge 3. Systems and Survival.
Operating practically in space fundamentally changed the game for tactical evasion. The Soviet MiG-25 was their absolute fastest, top-tier interceptor. It could hit Mach 2.83, but its ceiling tapped out at 62,000 feet. The Blackbird cruised at Mach 3.2 at 85,000 feet. As the source points out, this gap wasn't just a marginal difference, it was structural. The fastest Soviet interceptor physically could not breathe the air where the Blackbird lived. No aircraft could reach the altitude, and no missile could close that kind of speed differential.
To really grasp how perfectly they nailed this engineering brief, think about this. During the Vietnam War, North Vietnamese air defense forces fired approximately 800 surface-to-air missiles at the SR-71. 800 attempts to shoot it down. So, how many actually connected? 0. Literally, not a single one. The geometry of the engagement was just completely impossible for the enemy. Think about it. By the time a radar site acquired the Blackbird, computed a firing solution, launched the missile, and that missile burned through its propellant trying to climb to 80,000 feet, the SR-71 was simply gone. The standard evasive maneuver wasn't a sharp bank or dropping a bunch of flares. It was just throttle advancement. The crew just pushed the throttles forward. That's it. Nothing else was required.
Which brings us to the unbroken record and the incredible legacy of this machine.
Just to give you some everyday context for what Mach 3.2 actually means for travel time, let's look at a standard commercial flight from New York to London. That usually takes you about 7 hours, right? The SR-71 covered that exact same distance in 1 hour and 54 minutes. Or how about a cross-country flight from LA to Washington, D.C., normally 5 hours? The Blackbird did it in 64 minutes and 20 seconds. It completely collapsed our understanding of geography.
Now, they did eventually retire the Blackbird for good in 1999, but, and this is crucial to understand, it wasn't retired because it became vulnerable. It never was. The retirement was mostly driven by economics. Operating costs were just astronomically high. On top of that, the film-based intelligence it gathered couldn't be transmitted in real time to commanders on the ground. And finally, the dawn of the modern satellite era meant reconnaissance satellites could offer persistent, 24/7 coverage over denied territories without ever risking a human crew.
So, wrapping up our main takeaways from the source material for this explainer, the SR-71 Blackbird was an aircraft born strictly out of necessity. It was an absolutely impossible engineering brief that pushed every available material, propulsion, and systems technology to its absolute limit, all at the exact same time. From the covertly sourced titanium to the airframe that literally sealed itself using the intense heat of friction to an engine that transformed its operating principles 3 times in a single flight, none of those solutions were obvious, but all of them were completely necessary to solve those 3 massive challenges. Today, we live in a world of drones, highly advanced satellites, and directed energy. Manned reconnaissance at these extreme speeds just isn't a modern strategic priority anymore. But it does leave us with a totally fascinating open engineering question to end on. If the threat environment suddenly required it again, if speed and altitude became the absolute only viable protection, could today's engineers build something faster? It's definitely something incredible to think about. Thanks for joining me on this explainer. I hope you learned as much as I did.